greater than 50%, often in the greater than 90% likelihood that the next access you want to do is somewhere else in some other memory. And that means that the useful bandwidth that the processor can actually achieve is limited to the network's bandwidth, not to the memory system's bandwidth. And that really causes processing to come to a crawl, because you may have, despite the fact that you've got a 3 GHz processor with huge caches and everything else, everything is just limited to the rate that you can access data across the network. So the EMU computer, which we actually term memory web, has been designed specifically to deal with this problem. So we support fully random access to individual words of data instead of to cache line sized blocks. And that's important because if your data accesses are scattered all over the place, while the processor always reads a cache line full of data, which is typically 64 to 1 KB of data depending on the specific processor architecture, it only uses 8 or 16 bytes of that access, and the rest is just wasted. So instead of having wide memory channels, we have a large number of narrow memory channels. And we use multi-threaded cores. Each CPU core actually simultaneously processes 64 separate threads, alternating on a cycle-by-cycle basis. Now this lets us hide nearly all latency, and it lets us avoid having bypass stages and hazards in our processor pipeline as well. The energy consumption using this approach is reduced because we're not wasting any data. So we're moving only the data we want, and we don't waste any energy moving data that we don't want. And we also are able, because these memory systems are small, we can place the cores physically very close to the memory that they control, and thereby the distance you're moving the data is reduced. We connect the nodes with a high radix rapid I/O network into a system-wide PGAS address space that's scalable actually up to 64,000 endpoints and 512,000 memory channels. And the memory size and the memory bandwidth all scale up. As you add more nodes, you get uniform blocks of all of those, and the nature of the way this thing works, it scales smoothly, and you don't end up with bottlenecks as the system gets bigger. And in addition, the Silk programming environment we use lends itself to writing programs that scale nicely up to very large sizes, and we'll talk more about that as we go along. So there's a fundamental concept that dates back to a very old proverb that says, if the mountain won't come to you, you should go to the mountain. So I claim that most computers insist on the mountain coming to them. Because let's say you have a database that's a terabyte of data, which is not very big by big data standards, but now, and then we have a program that operates on that data. How big do you think a typical program is that operates on something like this? A megabyte, say? Often less. So we have a program that's a megabyte. We have data that's 1 million times bigger than a megabyte. But we sit there on a regular computer, and the program's processing the data, so all of the data has got to come to where the program is. So we're moving typically the entire database or a substantial portion of it across the network to get it to where this program is running on a core. And it seems not the most efficient choice. So EMU does something a little different. What we do is we move the program, or actually specifically the execution context of the program, to where the data it wants to process is. So as soon as we do a memory reference that's not in the memory that the current CPU controls, we actually pack up the program context consisting of a program counter and whatever registers are live and ship them in a packet across the network and restart it on a computer that's connected directly to the memory that contains the data we want. So if you do this and analyze the total amount of data that's moved across the network, it tends to be reduced by something like a factor of 50 on most applications compared to moving all the data. So that's a pretty big gain, especially when you consider that network technology does not follow anything like Moore's Law. It's growth in network bandwidth maybe doubles every 5 years or so at best. And CPUs, even though Moore's Law is arguably dead at this point, are still advancing faster than that. So the other advantage of this is that data movement across the network is a one-way trip. Normally, if you're reading data, you send out a read request, the data comes back. It takes a long time and more complicated to manage because you have to associate the response with the original request. For us, all network traffic is one way. We send program contexts across the network. They arrive, and other than hardware error correction type of issues, nothing ever gets sent back across the network. We do actually support writing across the network, since that's also a one-way trip and it's convenient to do that. But no read ever goes across our system network at all. This whole thing's pretty much invisible to the programmer. You write a program, it doesn't really need to worry about where the data it wants to access resides. You reference it. If it's on a different node, the context moves. The programmer doesn't see that. It just starts up again at the right place and continues, and the programmer never knows that the move occurred at all. Now, real world, the programmer sometimes wants to know that, so we have ways for the programmer to find out if he wants to know. But you can write a program that's completely correct and gives decent performance, being completely oblivious to the placement of data. If you want to optimize it, you probably do want to do some placement-based optimizations, but it's not absolutely necessary. As long as you have enough threads active, though, you don't see any latency. All instructions, even memory references, appear to the programmer to take a single clock to execute, as long as there's enough threads to hide the latency. And that makes it really easy to do upfront analysis of what performance you're going to get on a program. We can actually write programs, run them through a tool that we have that generates a sort of a virtual trace of what's going to happen, how many memory references, how many instructions between memory references, things like that. And they can accurately predict within under 10% the speed the program will actually execute when you run it on the machine.
You mentioned at the beginning that you maybe hide all of the latency. How does that change as you go to the larger scale system?
The latency remains hidden as long as there's enough threads to hide it. The place where you actually latency becomes visible is if you only have, well, each processor core can execute 64 threads, as I mentioned at once. If you drop down below about 32 threads executing on the core, you start to see that loads take more than one cycle to happen. And if you drop down below 16, you start to see that certain long-running instructions like divides take time to happen. And like down at like 12, 10, some of the other instructions like floating point, multiply, add start to pop up. But as soon as you cross over 32 threads on the core, it appears that everything takes one cycle no matter what. Yes?
If you have enough threads, in terms of latency, you can even hide the latency of shipping data to where the process is, instead of shipping the process to where
Well, that's a lot harder because threads necessarily stall when you're waiting for a read. And at least, the practical aspect of the way you design a processor, it's virtually impossible to save away the context of a thread and do something else when it's waiting for a read response. You can have a few threads in there that will run instead while that's happening, but given that remote read takes thousands of clocks, you run out of things you can use to hide that latency. So it's very unusual to actually be able to effectively hide remote reads and even local reads on realistic systems. Like if you take a Xeon processor, for example, it will issue 4 read requests at once. That's outstanding from each thread, and once it's done that, there's nothing else it can do till the data comes back. So, given that even the local memory latency is hundreds of clocks, you stall in effect anytime you miss in cache, and that becomes very visible. Yes?
What is the size of your local memory?
Local memory is 64 gigabytes.
And that's implemented as just commodity DRAM?
Yes, DDR4 DRAM.
What is the maximum number of CPUs your system can scale to?
We can scale to 512,000 CPUs.
So I understand it's difficult to hide the latency with 64 threads with GPUs or 20,000 threads on chips.
Yes, GPUs.
20,000 threads, still you cannot hide the latency.
Well, GPUs do not hide latency very well. They issue a lot of requests in parallel, but once they've issued all those requests, they stall and wait for the data. They issue a lot of requests simultaneously, but they still spend a lot of time stalled.
Why? Because they don't have any more going on.
GPUs are in order execution on any given thread, and if all the threads issue a memory request, all the threads now stop and wait for the data to come back. And they're very much bound to local memory. GPUs do not have any capability to look into, directly access a large address space that spans across multiple machines.
No, I'm not saying that you should never use GPUs. I'm saying if you had your parallel processor, instead of 64 threads, you have 20,000 threads. You still needed to ship computation to the data.
Yes, you definitely would, because you could have lots of threads, but the threads still cannot hide the latency of remote access. It's just it's impractical to keep track of that many requests, and the latency is just enormous for going across a network by comparison to processor clock rate. So we term our architecture the put-only architecture because, as I mentioned, network traffic is one way. We have no transactions on the network that require a response. And it's interesting that, in fact, the size of a context is slightly smaller than the size of a cache line on a typical processor. So you're pretty much even even in the case that you do one memory reference at a particular bank of memory and then move to a different one, that's pretty much a break even with a typical cache-based system. As soon as you can even do 2 references at the same location, you have about a 2-to-1 advantage. And what we find realistically with well-written programs is that we can do on the order of 5 to 10 memory references within a 64 gigabyte bank of memory before we move to a different one. So that gives us quite a large advantage over a cache-based system. It also makes having the one-way network means that we don't need to deal with virtual channels and things like that, which greatly simplifies network design as well. Yes?
So, does you have a limited number of registers for you to achieve that, or do you
The C-
specify specific locations in the program where you know that some registers are dead and you can migrate?
Okay, the CPU has 16 general purpose registers plus a couple of other control registers. That's what makes up the packet that gets transmitted. And we actually have a ability to dynamically resize the packet that we transmit to only transmit live registers with some help from the compiler. The compiler if the compiler knows or the programmer knows and inserts a pragma that tells the compiler that a migration is expected at a certain point, the compiler issues a machine instruction called resize with a bit mask that says which registers are live, and the context that's transmitted across the network is then reduced to only the live registers. So we don't have to transmit all 16 general purpose registers. On average, we seem to find that most contexts that gets transmitted are on the order of about 7 to 12 words, and average is probably about 9 or so most of the time.
So where do you keep the stack?
The stack is kept at the place where the routine is called initially. We build a cactus stack so that as it needs to grow, we can actually add more pieces to it wherever we are at the time when we have exceeded the size of a block. One of the important compiler optimizations, though, is to actually minimize stack references. And this is a little bit different optimization than most compilers use. So we've played some new territory here. But stack references are expensive because they tend to cause extra migrations if you've moved away from where you were when the stack frame was created. So the compiler tries really hard, even at the expense of additional instructions, to keep everything in the registers that it can, and avoid making references to the stack whenever possible. So one thing I did that is sort of an added feature that's not kind of fundamental to the architecture is that we do remote writes across the network. So by being able to write across the network, we cut the total number of migrations by almost half compared to if we migrated for both reads and writes. And we also are able to use a technique called a fenced write, which allows us to guarantee that the write has actually been delivered at the far end without having to stall on each individual write. We count how many writes are outstanding, and when acknowledges come back from the writes, we insert a fence operation when we want to know that a sequence of writes is completed, and we'll stall only once for the whole sequence rather than on each write individually. It's important for producer-consumer type problems where we have to deliver a message to the far end. So we've coined a term called weak and strong locality in the course of developing this system. So strong locality is the locality most people talk about all the time, which is locality that's related to the size of a cache line. In a cache-based system, locality the only locality the system can actually take significant advantage of is the size of a cache line. Anything spread further apart than that, it doesn't help you at all. And it's actually quantized on the cache line boundary. So even if you've got two adjacent words, if they're in two different cache lines, there's no benefit to be had. In our system, we don't care at all about cache line level granularity. We have a much weaker constraint, which is the size of an entire memory bank, which on our first system is 64 gigabytes. So finding some locality in a 64 gigabyte block is an awful lot easier than finding it in 128 bytes. And it's a very rare program that doesn't exhibit some weak locality, even if it has virtually no strong locality. And it's often pretty easy to reorder things, and even if you don't start out with weak locality, you can reorder things just a little bit to get it most of the time. So let's shift gears a bit and take a look at what the architecture of the system actually is. So our system consists of nodes that are connected by a high radix rapid I/O network. It's actually a fat tree if the network gets large enough to need it to be actually implemented as a tree. So each node has a thing in it called a migration engine, which is essentially a crossbar switch that moves things between cores in the node and between nodes. It also has connected to the migration engine a thing called the stationary core. Now, the stationary core is a conventional processor that runs processes that don't migrate, and we use it primarily to run the operating system and system services. We really don't run application code on there at this point in time, although it's possible in the future we might run some application code there. Then we have in each node 8 what we call Gossamer nodelets. A nodelet has 4 CPU cores. Each core, as I said, supports 64 threads at once, and 1 bank of memory. So the 4 cores share a bank of memory, and this is just an engineering exercise of matching the bandwidth that the cores can consume with the bandwidth the memory system has. So each node actually has 8 nodelets in it, and threads migrate both from one nodelet to another within the node or between nodes, and to the programmer which one of those is happening is completely invisible. And the fact that nodelets and nodes aren't equal is just a consequence of, again, an engineering issue of what fits in the FPGAs that we're using to implement the system. So the stationary cores are basically a supervisory function. They perform I/O, execute the operating system. They run the terminal interface, and when you type the name of a program on your Linux terminal, the stationary core spawns threads on the Gossamer cores to actually execute. The Gossamer cores execute the threads, do essentially all the user-level computation, and the threads migrate from nodelet to nodelet as needed as the program executes. When they need to perform a system service like I/O, when they need when they take an exception, or when they terminate, they return to the stationary core to handle all of those conditions. So the core architecture, we have a deeply pipelined 64-way multi-threaded core. It's an accumulator plus 16 general registers. It supports atomic operations on memory at an instruction level. As we talked about, non-local memory references cause migrations, and context is, in hardware, moved to a thing called a migration queue, which moves it out. And I'll show you a diagram of this in a minute. There's an actual machine instruction called spawn, which causes creation of a new thread. And there's another instruction called release that moves the context from execution into a service queue where it will be transferred to the stationary core for processing. There's a thing called a run queue, which is threads that are waiting to run on a core. The core pulls threads out of the run queue when a space frees up, and places threads in the run queue, back in the run queue when they get swapped out for some reason. Incoming threads, as they move in from other nodes, are placed in the run queue by the migration engine. And all thread scheduling is automatic and performed by the hardware without any intervention at all of any kind of software. So this is a little more detailed look at the node architecture. There, you'll see there's three fundamental queues here connected to the core. So the run queue is the input to the cores of new context to be executed, and threads that leave the cores are either placed in the service queue if they need service by the stationary core, or the migration queue if they're trying to migrate to a different node. The migration engine takes things out of the migration queue and puts things into the run queue, and decides whether it's going to a different nodelet in the same node or out to a different node across the network. So here's a quick look at the actual products we're making that supports this. So our first product we call the chick, that's the baby emu, and this is it's basically a tower type of case that can stand beside your desk. It runs at 110 volt power. It delivers 2.2 GUPS on the random access memory benchmark, and it also can do breadth first search at about 5 gigatips, which is comparable to a full rack of Xeons. We're actually in the process of building the first one of these right now. We'll be delivering the first 2 systems to a customer this September, and general availability will start in October. Then we have the EMU1 server, which is a larger implementation that uses identical node cards, but a more elaborate network and much greater packing density. So instead of a little 8-node motherboard that we have here, we have a 32-node motherboard in the rack, and then we have 8 of those motherboards, and these are network switches, rapid I/O switches up here. So we'll be starting to deliver these around the first of the year, and these are actually scalable all the way up, as I said, to 64,000 nodes and 512,000 of the 512,000 nodelets, which is actually 2 million cores. Yes?
So, let's suppose if you have 2 different geographical locations where you have 2 database and you are copying your same program to react to both these joint database which are very far in the network. Now, let's suppose problem is about joining a table from 2 different locations. So how do you do that? Because till now I think that in copying the program near to the database, it is a single thing and it is very fast.
Well, the program actually, there's a copy in every bank of memory. We assume the program's small. We have each bank's got 64 gigabytes. If 1 megabyte of that is taken up by a program, who cares? So the program never moves. If you want to do a join, for example, I think you're asking, so that gets typically will be performed by the threads migrate around to build the things that get joined, and then use remote writes or remote atomic operations to actually move the data to the final place where it's going to reside. Does that help you? Okay, so how do you program this machine? So the biggest problem with this machine is that it doesn't work like the computers you're used to. That's fairly clear. So you need to it takes some thought to think about how you actually program it and what language is most appropriate to program it in. Now, clearly it's a computer. You could, in principle, run any language on it, and but we put a great deal of effort into thinking about what language is best to start with that matches the underlying architecture well. So we determined that Silk is the place we wanted to start. Now, you all familiar with Silk, or know what it is at least?
Intel Silk?
Well, Intel Silk is, well, what we're supporting is similar to Intel Silk, but it isn't actually, it's actually more akin to the original Silk that came out of MIT. Although it does have some of the Intel extensions in it, but we don't have the vector extensions included. And we do have some other extensions that we've added. But Intel Silk, we actually are using as our base the Intel Silk compiler, in fact. So for those who aren't familiar, so Silk is basically C with 3 added commands. The commands that you add are called Silk Spawn, Silk Sync, and Silk 4. And I'll talk a little more in detail about those momentarily. Other than that, it's C, and in fact, you can run any C program on our machine without changing it. Of course, there will be a sequential program, which will not be the best use of the machine. But we can run any C program, which makes it relatively easy to port things, because a lot of the functions that don't need to actually be parallelized, the leaf level functions are just C functions, and they move over directly. We're using a LLVM, the Intel Silk front end with the LLVM back end to generate our code. And as I mentioned earlier, the key optimization we do, which we had to design our own optimization passes around, is minimizing register spills to the stack, because that is one of the biggest performance limiters that we found. We've also added a capability that we define what we call views of memory. We can create a memory segment where instead of the memory accesses being address 1, address 2, 3, 4 is all on one node in a straight line, and then address 1,000,001 goes to the next node. We can stripe the data across the memory systems in various ways. So you could build an array where element 0 is on node 0, element 1 is on node 1, element 2 is on node 2, things like that. Or you can also make it 0 and 1 on one node, 2 and 3 on the next. You can also do things like start element 0 on node 27 and then have them go around, which sounds like a weird thing to do, but it turns out to be really useful if you have 2 arrays and they have sort of a funny relationship with each other for starting points. So these are things that we've done to make it a little easier to manage the placement of data for effective processing. And you can write your program separately from laying out the data, which is really helpful, because you can write the program and then change the layout of the data, leaving the rest of the program untouched, and optimize things.
So with your ability to hide latency and with a rigid, I guess, round-robin execution of the threads, what, other than maybe energy usage advantage, does messing with the memory layout give you?
Well, the program will as a whole will execute faster if you reduce the number of migrations. So each thread doesn't see any latency, but the latency is in fact present. So the overall wall clock time to do 1,000 threads, 10,000 threads, whatever it is, will be smaller if the total number of migrations is reduced. And
It's basically the total amount of data you're moving divided by the bandwidth, essentially.
yes. So there's advantages to this. There's also advantages just in terms of simplifying the way you think about things, to have it laid out in different ways. We also have a capability that's important for in-memory databases that we have, and this is really an operating system function. We've created a way to create data structures, allocate data structures and initialize them that are not terminated when the program terminates. So you can leave data in memory with a system call, and the program ends and you can run another program against the same data set that's still resident in memory, which is very helpful to these large data sets. And then we also, of course, have other functions that let you release the data when you want to, or spool it out to disk, or whatever is needed. But the idea of persistent data is important when you've got terabytes of main memory in the system, and you don't want to actually load it all from disk every time you start a program. So Silk language, we have three main keywords. I said silk spawn, variable equal function. That creates a child thread that executes the function, and the parent thread continues asynchronously. Now, the result of the parent doing a spawn is normally going to be exactly the same as the result of just the parent calling the child, so that as long as you adhere to the basic underlying Silk rules, you'll find that you can execute the program sequentially or in parallel and get the same answer. There are some exceptions having to do mostly with floating point numbers, where the order you do things matter, and with shared variables can allow you to create race conditions. But if you don't use any shared variables that are shared among child threads, it actually is pretty much impossible to create a race in Silk, and that's a very nice feature for getting your programs right. So Silk sync waits for the current, causes the parent to wait till all the children it has spawned have completed, and then yeah.
So is there an opportunity to not have to wait for all of them?
Well, in standard Silk, no. We actually have a function called Eureka that we've added that allows one child to inform all the other children that I found the answer, you can stop now. And that child, when it returns with a special function, actually picks up the continuation as soon as it returns, and all the other children are aborted. This is an extension. It's not officially part of Silk, but it's something we do support. Then Silk 4 is essentially a do-all type of function that takes a for loop and creates a thread for each iteration, or actually there's a thing called grain size that says how many iterations to put in each child. So if you have Silk 4 for I equals 0 to 1,000,000, you could say do 10,000 iterations per thread, or 1,000, or 2. Whatever's appropriate for what you're trying to do. There's also a secondary function called radix, which affects Silk 4, which is that if you're going to spawn a very large number of children to do a for loop, you don't really want to spawn them all from the same node where the parent is executing. So what you actually want to do is say set radix equals 16 or something, so you'll spawn 16 children, and each of those children will spawn 16 more children or something like that, so that the actual spawn operation gets done in parallel, and that can be important if you've got a for loop that's spawning 100,000 threads or something like that.
So what's sitting below Silk that we can program to? Like if you want to put another programming model, is there something that we would have to do, we can map to, or would we basically have to generate Silk and then compile that?
Well, there's two options at this point. There's generating Silk or generating LLVM intermediate representation, and we can handle either one. We're looking at, and actually have put in a proposal for a grant to develop a translator that will translate C with OpenMP calls into Silk, which would make porting of C programs that use OpenMP much easier. And we hope we'll get some funding from the government to pay for that.
But OpenMP's got a lot more awareness of scheduling and placement still, so it's like you're throwing a lot of information away.
Yes, you'd probably be throwing considerable information away. But we don't.
OpenMP claim, what's up, LLVMIR.
Yeah, you can actually, if you can get LLVMIR out of it, that's probably how you would, or that's one way you can do it. There's a number of options, and we do expect that we hope by this time next year we'll have considerably more flexibility in what you can use for source code. We don't at present support inlet, which was part of the original Silk definition. In discussion with Charles Leiserson, he sort of agreed that inlet might have been a bad idea because very few people ever understood what it was supposed to do, and they therefore tended to cause them more aggravation than anything else, because they tended to lead to incorrect programs being generated. So most of the Silk programs that have been written don't use inlet anyway, and it's complicated to implement, so we elected not to. And Intel Silk does not support inlet. We are supporting, or will be in the near future, we're still debugging it, a variant of Silk Sync that actually includes a reduction function, where as soon as a thread returns to the sync point, the reduction function is called on the value it returns to add it to, or to reduce it into a variable that's in the parent's namespace. And that lets that reduction happen in the time between when the child completes and the rest of the children complete the barrier. So it's pretty efficient, and programmers find it pretty nice and conceptually to think about it that way. It isn't actually doing anything that couldn't be done other ways, but it does seem to simplify the programming problem. And right now we're just doing straight C, but we will eventually have full C++. It's more just a question of getting all the libraries ported. Now, one thing about our Silk that's kind of interesting is the original Silk used a work stealing concept, where actually what would happen in traditional Silk, you create some fixed number of threads depending on the size of the system and what resources it has, and the actual work gets executed within that fixed number of threads. So when you spawn, you have a pool of threads that are waiting for work to do, and they execute the particular thread, and then the particular Silk function that's been spawned, and when it returns, that thread becomes free to pick up something else. Now, since we have hardware that creates and destroys threads very efficiently, that the software overhead of managing all of that was deemed to be not very useful. So we actually, when you do a spawn, we actually create a new thread, and when the thread returns, the thread actually dies. So that's a little bit different. The only place that resembles the work stealing concept is when the parent reaches a sync point. If the parent reaches its sync point before all of the children have finished, the parent saves its context into a data structure, and the last child to complete actually assumes the identity of the parent rather than having the parent busy wait. So it frees up the parent's context while it's waiting at the barrier. So we also have mechanisms where a thread can voluntarily place itself at the back of the run queue, so that if it's waiting for some event to happen, there's no reason for it to tie up execution context. The total number of threads is really only limited by the available memory, and we give the programmer a view that's as far as we know, completely indistinguishable from the one they see programming in a regular Silk environment. So a couple of things we do that is a little different, that's consequence of the migration model, is if you do a Silk spawn where the function that you're spawning has arguments, we will try to create the thread on the proper node where its arguments live. So if the first memory argument that's a pointer is pointing at a different node than the one where the parent runs, the thread will actually be created on the node where that address lives. If there's more than one address in the argument list, it just picks the leftmost one to do this. And if there are no pointers in the argument list, it's just going to create the child on the same node as the parent. We have intrinsic functions that force the generation of atomic operations. We have a pretty rich set of atomics implemented in hardware. We have add to memory, AND or XOR with memory, minimum and maximum, and compare and swap. So this lets you implement a huge array of locking and lock-free data structures with very good program control and very high efficiency. One thing also that we do that's kind of interesting is that common problem in data structures that have locks is that if a thread gets interrupted while holding a lock, everyone else that's waiting to access that data structure is going to wait the entire time that thread is swapped out. And most systems have a problem that they can't disable interrupts at user level because that's considered a security violation. We actually created a mechanism that lets us disable interrupts at user level with a fixed timer. So we have a time slice interrupt that kicks threads out periodically to allow fairness and guarantee everyone gets some time slices. So you're allowed to disable interrupts for up to one time slice at a time. If you're holding interrupts disabled for more than one time slice, when the second time slice interrupt happens, your thread gets aborted. So you have to be a good citizen and guarantee that you're not going to turn off interrupts for 2 time slices. But normally in a locking data structure, if you're programming it right, you will only expect to hold off interrupts for a few tens of instructions at most. So this shouldn't be an issue in a properly written program, and it does guarantee that the application will not get interrupted while holding a lock, which makes programming of these data, a lot of these functions, a lot easier to do properly. Other things. So system software, we're running standard CentOS Linux on the stationary core. So very familiar environment there. The operating system runs on the stationary core, and at this point, main and all of its children run on Gossamer cores. We're looking at, and probably will implement in the future, the ability to specify that main and or certain things that main calls will run on the stationary cores as well. But we don't provide that at this point in time. The runtime executes mainly on the stationary cores. There are some runtime functions that do execute on the Gossamer cores. There's some things that migrate around the system, doing garbage collection or informing. There's tables of status, like how many threads are executing on each nodelet in the system, which we have a thread that runs around the system updating that table all around. So if the programmer wants to do introspection where they find out what's the least busy node in case they want to dispatch work to a place that's not busy, for example, there's intrinsic functions we provide to access that information, and we have threads that run around the system in the background keeping the information up to date. Upon completion, all the threads ultimately return to main, and main returns to Linux as you would expect in a normal environment. So our current system design is nearly complete. We're laying out our boards right now, and actually that'll be finished probably by the end of May, and we'll actually release our boards for fabrication. We expect to have a working prototype in July, and as I mentioned, we'll be delivering 2 systems to a customer in September. We're seeing performance that's on the order of 10x better than commercial systems on GUPS and BFS and similar applications. We've found the system does really well at gene sequencing. We can get really dramatic improvements over conventional computers for applications like that. It's also really good for dealing with parallel I/O at high rates because we connect a lot of I/O channels to the different nodes. So one application we're looking at is real-time stock market valuation, where you're getting feeds coming in of every stock trade, and you're continuously doing portfolio valuation across the entire market in real time. We're very much interested in expanding our application base and expanding our libraries, and very interested in collaboration with universities and research organizations for creation of libraries and public domain applications, and we'd love to collaborate with anyone here in any of those areas. So just to wrap up, so we can support enormous problems in memory and with real-time updates. Applications that kill processors that use caches work best on our system, but we also work well on systems that work on problems that work well on systems with caches, but our advantage is less there. We make much better use of system bandwidth than conventional processors, so this both increases performance and reduces energy consumption, and we can deal with gigantic levels of parallelism, and the programming environment really supports programming with gigantic levels of parallelism. And we found that if you're familiar with programming in parallel and OpenMP, for example, or MPI, it doesn't really take more than a couple days to become fairly proficient at programming our system. Obviously, it takes more than a couple days to become expert, but it's not hard to learn. We've had people that actually started programming on it and successfully wrote acceptable programs, not amazing programs, the same day. So that's about it. This is our team, and growing all the time, but all very highly skilled people in their field that with many years of experience, or most of them have many years of experience. We also have several recent graduates among the team, and actually looking now, most of our new hires we're expecting to be more recent graduates for a while, so there's opportunities there as well. And that's it. I'd like to thank you all, and happy to answer any questions. Yes? We're currently using a IBM Power processor as our stationary core. There's no particular reason for that choice, other than that it was available to us at a reasonable price and fit well with some relatively trivial engineering reasons. We considered using Intel, we considered using ARM. We could change it at very little work to something else. It would be fine.
Just from pure local operation, no migration involved, how does the performance of a single decimal core compare to a regular Xeon core?
So it's much lower.
It's FPGA.
It's an FPGA, it's running at 300 megahertz, and it can run 64 threads concurrently, but you one core is considerably less than the Xeon. Probably,
One time.
with 64 threads running, it probably is about 1/8 or so what a Xeon would do. We do expect to build a second generation that will be based on ASIC, will run its clock rates comparable to the Xeon. But that's a ways away because we need to get product to market and get enough funding to actually pay for the development of ASIC.
I have a cache breaker application, as you call it. Is there a way for me to try it on the
Yeah,
machine?
yeah, get in touch with me and we'll see what we work out. Yeah.
It might be a worst case because it keeps on accessing 2 bits using atomic operations across a arbitrarily large address space.
I think we would probably do really well with that.
How do you handle virtual memory on the?
So we don't really have virtual memory. All the memory is physical. We have a fairly rudimentary level of segmentation-based accuracy where you can create, there's actually 256 different application IDs in the system. Application ID 0 is the operating system, but so you can have 255 user applications, and we have segments of registers that allow granting access to certain portions of memory to different applications, or sharing certain portions among applications. But there is no notion of like demand paging or anything like that. Yes.
Would it be a fair statement to say that in terms of workloads you're targeting, you're fairly similar to create Eureka machines?
Yes, it would be somewhat similar to that.
How do you compare what's your main selling point over create GPU?
Well, we could blow the doors off of Eureka on almost any application that we've seen. That's our main selling point. We're 10 times faster or more. So,
Even with FPGA.
yes.
So it takes faster for BFS also, but that depends on the type of the graph itself.
Well, it varies with the graph. I mean, if you've got a graph that's very, very well behaved in terms of access pattern, then we won't be 10 times faster. But if you do a random graph using if you do the BFS benchmark, the graph 500 benchmark that generates a graph randomly, we tend to get really good performance compared to Eureka or pretty much any other machine.
So what happens with the very skinny graphs, the line graph? You need a cache in order to get some performance, but we do not have one.
So we don't have a cache, and there's times when it would be nice if we had one, for sure.
Right, so if you have very low parallelism, then if you had a cache, then that would have been helpful. Right?
Yeah, so we've thought about implementing various forms of caches, and we very well might in the next generation. One thing that's, I mean, company right now is got 14 people, and so we've concentrated on getting something out that's good for a certain class of application, and we recognize its top limitations. We're learning what those are, and our next generation will have more capabilities. There's a thing called a carpet bag cache, which is actually a migrating cache that we're looking at. There's also a notion of having a local cache that is that caches things that you use when you're at a certain node that stays on the node. We might implement either one of those. We do, by the way, have instruction cache, and we'll talk about that. The instruction cache is there. It's actually very important because typically all threads, or many of the threads that are running, are actually executing the same code. So we get very high hit rates on the instruction cache because they're all shared cache, and we don't have to have each thread constantly fetching its own code from memory.
So my question is,
Right.
if it is local, right? So energy consumption will reduce.
Mhm. Yeah, energy, if you, migrations are definitely consume considerable energy. Transmitting across the network uses a lot of energy compared to most other things. And there's another effect that I didn't go into in detail that, that hurts performance with a lot of migrations, which is it takes finite time to unload a thread out of the out of one processor and load it into another. So, and during that time, one of the execution contexts is tied up because you're reading the data out of it or writing the data into it. So if you have too many migrations, you may find that more than half of your execution contexts are actually in the process of migrating rather than in the process of executing, so that you start to lose latency timing because you've got an enormous number of them that are being migrated. So it is important to minimize migrations for all sorts of reasons. And, you know, that's a big part of the skill of the programmer and or skill of the compiler. So not more migrations than are required for your application.
Does a single customer node have a few hundred cores?
So each node is one FPGA. It's got 32 cores in it. And it's got 8 nodelets, each node more than 4 cores. Each core, of course, like I said, runs 64 contacts. So in essence, a nodelet runs 256 contacts.
It reminds me a little bit of the Intel Xeon 5.
Yeah, it's got some similarities there. I mean, the biggest thing, the only thing we really do that's dramatically different from what other computers do is the migration. Everything else, you can find another example of a computer that does the same thing. But the migration thing is quite significant and really quite different from anything anyone else does.
So you're not interested in selling a single node for people who just want to play with many core applications? Sorry, highly multi-threaded.
Not at this point. I mean, we've talked to someone about it, but right now we're thinking the smallest thing we sell is the chick, which is 8 nodes.
And the largest machine you've actually built and operated, how much memory did that have in total?
Okay, we haven't actually got anything working yet. The physical hardware is, as I said, coming back in June to make sure something works in July. And that first machine is a chip. We'll be coming out with the full rack system around the beginning of next year. And that will have 256 nodes, which is 2,000 cores. And it will be scalable to multiple racks if you want.
It's about 16 terabyte of memory for one rack.
Yeah, that's right. No, that's not right. That's 16 terabytes per tray, per 32 node tray. In the rack, it's 8 times that. It's 128 terabytes of memory in the rack.
That will be a single address space.
Yeah. Yeah, the whole thing is always a single address space, globally visible, which is one of the really nice things about it, because you can program it as completely flat memory and not have to worry about things too much.
So at one point you mentioned PGAS still, so where did the P come in?
It's partition global address space. It's partitioned in the sense that there are some unique spaces in there that are private, like the stationary core has private memory space that isn't globally visible, and then there's IO spaces that are private to each node. But it's essentially a flat address space shared with your machine.
But the data is statically mapped, the data itself is the migration of the threads and micro.
Right. Yeah, we really never migrate data other than initialization, or sometimes you make local copies. You've seen algorithms that work best if you make a local copy of a piece of data. It's a way to avoid a lot of future migrations. If you can do kind of a gap of data coming in from a lot of different nodes to one place to create a portion of your data set that can then be processed locally. In fact, when a multi-grid application, look at those, that sort of thing, where it builds the fine grid on one node, in essence, for each place that needs the fine grid. And that's a really effective way to process.
So what's the actual latency for migration? Like how many cycles? If you have thousands of core in your system.
The latency for what?
Oh, for migration.
Oh, migration, it'll depend on how far across the network you have
Yeah,
to
so
go.
what's the big
But it takes, okay, so the minimum time to do a migration, not counting the network, it's 2 times the number of registers to be migrated plus 4. So if you've got 10 registers, it takes 24 clocks. That's the load and unload time. And then depending on how far through the network you're going, it can be anywhere from about 100 nanoseconds minimum if you're actually migrating from one node on the same node to another, up to, well, I don't know, 10 microseconds or so in it. If you actually built a system with 64,000 endpoints, the largest system you can build, I believe the latency for that's about 10 microseconds.
So 64 thread per core can still hide that kind of latency.
Yes. Yeah, as long as you actually have all the cores having some of the threads like that, you can hide all the latency.
Since you're based on FPGAs, I guess it would be interesting for some people to be able to make custom extensions to the instruction set where they implement some special circuit in the FPGA.
Yes, it could, that could be done in principle. It's a challenging job. The FPGA as we have it is pretty full. Although fortunately Altera's coming out with a new model next year that's a little bigger, so it'll become more feasible when they come out with a larger FPGA. But even then it's complicated. It's taking a lot of risks to start modifying the instructions because and then it has to be plumbed through the compiler and everything. You notice you have no way to generate the new instructions. So this is always something that's an interesting question. Years and years ago, too many to count, I worked for a company called Guitar Computer, and one of our claims to fame, or our claims, maybe claims to infamy, was we sold a machine with a writable control store where the user could make their own instructions. And the option to actually do that was providing a special microassembler to let you generate your own instructions. It sold for a lot of money. So almost all of our customers bought the software to do that. Almost none of them ever used it. Or they usually tried it once and said, this is really hard. And that was the end of it.
FPGA development is really hard.
Yeah.
So it would seem like there are going to be some common operations that you would want to support if you continue with the FPGA. So like hashing, for example, is going to be massively slower in this type of architecture compared to another working machine. So, but you could add ISA extensions to provide CRC for hashing.
current instruction set is pretty kind of vanilla risk oriented, other than having things like spawn release instructions and atomic memory operations. And we're trying very hard to keep it simple because the other thing we found is the compiler is really pretty awful at dealing with complicated instructions. It just doesn't know how to generate code for that. So there's a lot of reasons why it's not as good as you think that it's special instructions.
Is it developed after an existing instruction set architecture, like a RISC-V or ARM or?
So our architecture is not that similar to that because mainly because it turned out to be easier to implement with the emulator style architecture. Although that was kind of locked in pretty early, and if I had to do over now, I think I would use a RISC-V architecture as a starting point, but that's not what we did. By the time we got to where we said maybe we should have done that, it was too late to go back without using a lot of ground. So my biggest conclusion of all this is the detailed instruction set architecture are not that important to where how the thing actually performs again. As proven by the